Hello, it's Mr. Waters, and here this is going to be a video where we're going to explore a little bit more about estimating distance. And this is specifically going to have to do with the more general situation where we think of distance, and I'll write it right here, we think of distance as a position that a particle is in relation to its starting point, how far it is away. So we're going to think of the distance, d of t, as the distance, how far away the particle is from its starting position at a given time. Okay? In other words, we could put it this way, the net distance. We've been introducing the idea of estimating areas under curves and estimating distances. We've been working with the idea that the particle, the person, the car, the whatever it is always walking away from its starting position. That is, that the distance and the time are always increasing, right? That the car may be speeding up, the car may be slowing down, the car may be going at a constant speed, but in any case, it's always going further, and at every point during the time interval, the distance is always increasing away from its starting point. Well, of course, they aren't necessarily. Okay, so what does that look like in terms of our calculus and our area calculations? So let's say we've got a situation here. We've got a guy who's going on a hike. It's John. John's going on a hike. John's going to be this color right here. Here's John. John is walking away from his house. And now he's not a very fast walker. John is walking 1 mile an hour. So John walks at 1 mile an hour. Okay, and this by the way is like a little distance timeline or number line here. And this is the distance in miles, right? Is what we're looking at here. Okay, so the distance in miles. We're going to go after 1 hour, since he's going 1 mile an hour, after 1 hour he's gone 1 mile, after 2 hours 2 miles, right? After 3 hours 3 miles, after 4 hours 4 miles, and after 5 miles he's gone 5 miles, right? Okay, he sits down because, it's a long walk, 5 miles. And so he sits down and he has his lunch and he goes, I think that's enough hiking for today. I think I want to go home. So he's right here, you understand. After 5 hours, here he is. It's his hat. All right, that he's using to shade his head. And now he's gone the first half of the walk. He walked like that. But now he's going to turn around and he's going to walk backwards. So now, what's that going to look like on a distance time graph down here, where we graph time versus d, which is, and let's be clear, John's distance from home. Okay. In other words, it's kind of a position, right? How far, not his total distance walked, but how far is he away from his house, right? So, John's walked this way, so at time 0, he was at 0. After 1 hour, he was 1 hour away. 2 hours, he was 2 hours away. 2 hours, he was, oops, wrong spot. 2 hours, he was 2 hours away. 3 hours, he was 3 miles away, right? Fix that. Okay. After 4 hours, he was 4 miles away. And after 5 miles, or after 5 hours, he's 5 miles away at his lunch spot. So he sits down, eats his lunch. Now he's going to go back. Now when he comes back this way, and I'm going to use green again, after another hour of travel, after 6 total hours of travel, he's actually now only, you understand, he's here now. He's only 4 miles from home. So now he's here 4 miles from home. Oops, 6 is right there. And after after 7 hours, he's actually only 3 miles from home. And after 8 hours, he's now only 2 miles from home. And after 9 hours, he's actually only 1 mile from home. And after 10 hours, he's back at home. And in effect, I mean, in terms of his net distance, he hasn't actually gone anywhere, right? He's ended up right back where he started. And so his net distance change, his position is equal to 0 again. Does that make sense? So now here is a distance function that measures d when d is his position function, his net distance from his starting point. Guys get that? Now that makes more sense if you think about money. Okay, so the first 5 hours, he's earning money. So the first 5 hours he earns $10, right? And then from 5 hours down to 10 hours, he spends his $5. So he earns $5, and then he spends $10. At the end of it, we don't think of it in terms of him having $10 somehow. We think, oh, he spent $5, he's earned $5, so his net dollars are now 0, right? So same thing here, his net travel distance is 0. So far, so good? Okay, now, so here is a graph of our position vector, right? Or rather, our position function, just like that. Okay, and we can see here, now what does this look like in terms of a speed graph? Well, down here, we're going to go ahead and we're going to make this speed graph, right? And he was always traveling, and this will be 1 mile an hour, 2 miles an hour. He was always traveling at 1 mile an hour for the entire distance traveled. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. For the first hour, he's traveling at 1 mile per hour. So I'll use, I wonder if you'd be able to see this. Oh, that looks a little light. Okay, we'll use this one again. Here is his speed graph, 1, 2, 3, 4, 5, up to 5 hours. He's traveling at a constant speed of 1 hour, right? Of 1 mile per hour. But then what happens when he turns around and walks backwards? Well, we usually think of that if you're walking backwards, we think of that speed as being negative, because we think of it this way. Remember when we did our rates of change, right? If we thought of of x as being, or d as being his distance from the house, if the distance from the house was shrinking, was getting smaller, we thought of that rate of change as being negative. Does that make sense? Okay. Also, if you look at our distance graph here, right here, that the slope of that line is 1 for 1 mile per hour, right? Plus 1 mile per hour. Over here, when the distance is decreasing, you can see the slope is negative because the distance is decreasing, right? D is decreasing, so the rate of change is negative. So we're going to think of that as negative 1 mile per hour. So where does that end up on our speed graph? Well, we're going to put that down here. Kind of like this. So here's negative 1 and there's negative 2. So starting at 5 up to 10, his speed was negative 1. Right? Now, what do we think about? Remember, these are the graphs we've been working with. This is the speed. And because we were walking backwards, because John's walking backwards, we had this negative speed. Now remember that we were calculating distances from these speed graphs by estimating the area under the curve. Well, let's see what that looks like from 0 to 5. Okay. You can see, oh look, it's a rectangle, so we don't have to do any fancy rectangle estimating thing. We can get the exact distance because the whole thing's a rectangle. Okay, the area of the rectangle is 5 times 1, right? It's equal to 5 miles. 5 miles per hour, or rather 1 mile per hour times 5 hours. We've got 5 miles. But what's this down here? Okay, we're still going to do, what's that distance mean? Okay, so I'm going to mark that off down here. Okay, so what's that distance down there? How do we think about that versus how we think about that? Well, we're going to multiply distance equals rate times time. But remember, the rate was -5. So the distance is 5 times -1, which we think of in terms of his net distance as negative. Okay? So, and you can see here that this -5, so if the area under the curve is the total distance, this +5, this -5 add together to give us a net distance of 0, which is what we observed here. That when John walked back to the house, his position was 0, the same position as when he had started, right? It's like we throw a ball up in the air, right? It starts out at 0, it goes up and it comes back down, and its position at the end of the travel, its height, is equal to 0, right? So his distance is 0, and so you notice that these two, this negative distance here and this positive distance, cancel each other out and give us a net distance of 0. Okay? Now, this is an aid of a concept about areas under curves. And I'm trying to justify this kind of general notion that we want to have about measuring areas under curves. That if the area under the curve is above the x-axis, that's a positive. Any area under the curve, or in this case above the curve, between the curve and the x-axis that's below the x-axis, that's a negative distance, and the two will cancel each other out when we're estimating areas under the curves. So an area above the curve, that's if the graph of the function is above the curve and the area goes down to the x-axis, that's positive. If the function graph is below the x-axis and the area is above the graph up to the x-axis, like here, we think of that as negative, and the two will cancel each other out. Okay? So, that's going to be very important for us. Okay, so I'm going to put this aside here. Put that down there. So think about this graph right here. Here you can see it. Here is I'm going to graph a sine curve from 0 to 2 pi. Right? There it is. So this is 2 pi. This is 3 pi over 2. Pi, and then that's pi over 2, -1, +1. Of course, our garden variety, y is equal to sine x. What is the area under the curve? what is total area under curve for y is equal to sine x from on the interval 0 to 2 pi? Well, take a minute to think about that. Put your video on pause if you need to, but take a minute to think about. If we were to somehow able to calculate this total area, what would it come out to be? Okay, hope you had a minute to think about that. If you said 0, you'd be correct. And why is that? Because this area, which is above the curve, and this area, which is below the curve, because of the symmetry of the sine curve, those two areas are exactly equal to each other. But this one is positive because it's above the x-axis. This one is negative because it's below the x-axis, and they exactly cancel each other out, just like John's net distance here. So the area under this curve is equal to 0. And you think about it, that makes sense, because this charts, if you think of back to our unit circle, this curve charts one, the point moving once around the unit circle, right? Here's our unit circle, right? What's the particle doing? From 0 to pi over 2, it's there. From pi over 2 to pi, it's there. So it's gone halfway around the circle. Now, it's going back again. 3 pi over 2, it's there. Back here, it started just like John at his house. It started right back where it started. And so, in effect, at least in terms of net distance traveled, net distance away from the 0 point there, it hasn't gone anywhere. Now, in terms of time, of course, it's gone 2 pi seconds or whatever. But the distance around the circle that it traveled, the net distance is 0 because it ended up where it started out. Okay? So we're going to call that one, that will be, John was example 1, so Mr. Sine curve is going to be example 2, right? Example 3, let's say we've got a constant speed graph that looks like this. And again, this will be speed here. This is positive, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4, like that. And what if, let's see, I'll just number it out like that. Okay, can we estimate the area under the curve here? Let's say it like this, right? And let's say it's, let's see here, like that. Okay, I suppose I should, well, so I suppose technically I should make that an open circle, but we won't worry about that. What's the net distance that this particle, if this is motion of a particle, and this is the speed of the particle, and this is the time, say in minutes, right? And this was 1, 2, 3, 4, that's going to be 5, 6, 7, 8, 9. So this will be 9 right there, right? So how far did the particle go? Well, measuring here, I'll use red for this one. I'll be consistent here about my colors. Okay, since it's a constant speed, can you see it's going to be 3 times 2, 6, right? Here, in effect, what the particle has done, what this represents, you understand, is the particle has stopped after 3, turned around, and gone back. It shows it on here, but because this is a speed, and it's giving the motion of the particle in terms of speed. Positive speed is forward travel. Negative speed, backwards travel. So what's happened here is, in terms of distance, is that things gone forward and then backwards. You guys get that? Okay. So what's the negative distance here? Or what's the, there's no such thing as negative distance. That's not right. The backwards distance is this right here. The backwards distance like that, which is the area of the curve, the area from the curve is below the x-axis and the area is from the curve up to the x-axis. Well, you can see that's 1, 2, 3, 4, and that's negative 4. 4 times negative 1, because this one was 4 times negative 1, which is negative 4, right? This one was 2 times 3, which is 6, right? And now we add them to get the net position change. Well, that's 6 plus negative 4, that's equal to 2. Okay? So if it's the time and distance graph, the net distance that person has gone is 2. Okay. Does that make sense? Okay, it's a very important point about taking integrals, that when we calculate them, area above will be positive, area below will be negative. Okay, that's enough. And I'm going to put a couple of homework problems for you to work on this time. And remember, later this morning, if you're already listening to this, okay, we're going to have our chat at 11 today. Bye.